In this video, we're going to explore a study of acceleration, but for general circular motion, rather than limiting ourselves to that nice radius 1 default speed for sine and cosine. So what we want to do is show that for any uniform speed circular motion, the acceleration must always be directly towards the center. Well, if we're going to do that, we'd better have a formula for general circular motion. And what we have there is we can start with our cos of t, and then our sine of t, and add some extra ingredients. With our t's in place, remember we can change our radius, so we're going to call that a. We already have an r, so we won't recycle that, but we have a, which defines our radius, and we have a second term that we can slide inside the expression here, and that b represents the rotational velocity, or scaling is probably a better term for that. It affects the velocity. It doesn't define the velocity, as we saw in an earlier example when we defined our own circle with a particular speed, but it does help or contribute to that speed calculation. So this would describe a circle with any radius we like and going around that circle at any speed we like in principle, and that will let us find a derivative, which is the velocity. And if we're careful with our calculations here, we always have the constant a, and we're going to have the derivative of cos, which is not cosine. It is negative sine of the same thing, bt, but we're going to get a chain rule multiplier of b coming out of that when we take the derivative of the inside. Likewise, when we take the derivative of sine bt, a sine bt, we get an a. We turn that sine into a cosine, and then we get a b multiplier. So we're going to have a times b and a times b. Let's actually write that out. So negative ab sine bt and positive ab cos bt for our velocity. And so our second derivative, which is equal to acceleration, is going to equal, same rule, we're going to get a b multiplier out, so it'll be negative ab squared, derivative of sine is cosine, and derivative of cosine is negative sine. We have a b, we're going to get another b from the chain rule, so b squared sine bt, and we see exactly the same pattern we saw in the last example, where we have r double prime equal to r, almost. R was just a cos bt, so if we factor out what we don't need, we actually have a negative b squared a cos bt. And we can do that for both the x and y terms. We have a negative and a b squared we can bring out front. And what that leaves is a sine bt. Now what we have is exactly our position vector with a multiplier out front. So our acceleration, second derivative, is simply equal to negative b squared times our position. Whatever position we're at, let's call that r of t. If we think of it as a vector, we don't usually, but here it's very helpful. That vector measured from the origin is our r of t. The acceleration vector will be in the opposite direction and scaled by b squared. Guess we should label that to make it clear. Opposite direction of r, and since r by definition points away from the origin, then it means that the acceleration points towards the origin or the center, and it'll be scaled by b squared. Again, the units are not really compatible, so lengths are hard to compare, but that b squared has something to do with how quickly we're spinning around the circle. The faster we go around the circle, larger b, faster we're moving around the circle means that the larger the acceleration needs to be. Again, thinking about that bending, if we're going to go fast around the circle, we need to really pull in with the centripetal force. If we're just leisurely, slowly moving around the circle, we don't need much bend to that curve. The acceleration would be smaller, corresponding to a smaller b value. So this analysis allows us to look at a very general form of circular motion and derive some of the important properties that you would see in a physics class, but looking at it from a rigorous mathematical perspective.